Okay, in this class, let us see about permanent magnets and electromagnets, the next topic, right? Now, what are permanent magnets, electromagnets, okay? What are their characteristics, all right? Now, how to choose, okay? How to choose a certain substance for making it to make it work like a permanent magnet, otherwise to make it work like an electromagnet. All these things we'll see it. Now, permanent magnet, let us discuss permanent magnet first. Now, permanent magnet, it is a substance, okay, so it is a substance or a material, right? Permanent magnet, it's simply a material, right? It's a substance which retain, okay, substance which retains its ferromagnetic property, which retains its ferromagnetic property for a longer time, okay, property for a longer time, okay. So this longer time, it usually you can call it as years, okay. So right, so a good example is, see, the normal magnet what you get it in your stationery shops, okay. If you go to a stationery shop and if you ask for a magnet set, so you will get a bar magnet, okay, then you will get a horseshoe magnet, right? I think all of you know about this, north and south pole, it will be like this, fine. Then you will get 2 or 3, one cuboid, okay, it will be like a small chip, right? And you will get again you'll be getting a cylindrical magnet. Again, it looks like a coin, okay, it looks like a coin. This looks like a small piece of chocolate, like that, okay. So this set, it is available for somewhere around 30 to 50 rupees, all right, fine. So this is what you get, right? Now, how are these things made, fine? So what can you, what substance can be used for permanent magnets? All those things we'll see here, okay. Now, substance which retains its ferromagnetic property for a longer time, okay. So these things are called as permanent magnets, okay. These things are called as permanent magnets. Now, what we have seen is that in the previous class, okay, so if you can remember, first we will take a fresh sample, so it is not magnetized at all, so the domains, they are in random direction. Now, when you keep it in the external magnetic field, that is, we kept it inside the solenoid, right? So what we saw was this external magnetic field, it will try to arrange the dipoles, or you can say the domain will grow in size. All the dipoles, it will start pointing in the direction of the external magnetic field. And once you reduce the current to 0, or otherwise when you make the magnetic field in the solenoid 0, even then you can see some magnetization, okay. So that iron piece, okay, for iron nail, for example, it will still have some magnetic property left in it, okay. So we will actually exploit that property to manufacture permanent magnets, okay. So that is why we have explicitly mentioned ferromagnetic property, all right, right. So permanent magnets, for manufacturing permanent magnets, we will mostly use, correct, we will mostly use ferromagnetic materials. We don't use diamagnetic or paramagnetic materials, all right, fine. So this is about permanent magnet. Now, if you take a look at the manufacturing process, okay, so manufacturing process, it's really easy. You don't have the detailed manufacturing process, just the basic idea, right? So if you take some earlier, okay, so you can say some 400 years ago, 400, 500 years back, so this the person who is making magnet, it is given in your NCERT book also, okay. So you have iron rod, okay, say you want to make that iron rod to act like a magnet, okay. Now you will keep this iron rod on the table, okay, you are keeping it on the table. Then what that person does is, he'll keep hammering it, okay, he'll keep hammering it, and before hammering you have to heat it, okay. This is a heated rod, this is actually a heated rod, okay. You will keep hammering it, keeping in the north-south direction, okay. So you have to, that one method they knew, okay, by trial and error or something. So they knew how to manufacture magnets, okay. So they used to keep this heated rod in the north-south direction, and they used to keep hammering. Now you may guess how this will actually turn that heated rod into magnet. Easy. So always, wherever, they at least they have noted that if you keep it in the north-south direction, okay, so if you keep it in the north-south direction, say the Earth's magnetic field, okay, for that heated rod, the Earth's magnetic field is the external field, right? So it will be in this direction. Now, since it is heated, what you will see is there will be so much of random thermal vibrations, correct? Now, when you keep hammering, okay, so because of the Earth's magnetic field. Okay, so the dipoles, right? So the dipoles in this heated rod, they will try to arrange in the direction of the Earth's magnetic field like this. Yeah, so they will try to arrange in the direction of the Earth's magnetic field. Okay, so this is heated rod. Right, so they will try to arrange in the direction of the Earth's magnetic field like this. Fine. Now once it cools down, okay, they will let it cool down after hammering. So they'll keep hammering for some time and they let it cool down. Now what you can notice is that once it cools down, right, once it cools down, the probability of these dipoles, okay, the probability of these dipoles going in any other direction, it will be really less, right? So once it cools down, when the temperature is coming down, the vibration will become much less, right? So once the vibration becomes much less, so almost all the dipoles, they will be in the direction of the Earth's magnetic field. So therefore you can say the iron rod is magnetized. Now it will start behaving like a magnet. Okay, now these things, they actually used it for your compass, magnetic compass. Fine. And you can also say for some experiments like that, right? Okay, so this was the earlier manufacturing process. Now as you know, what we saw here was we need some external magnetic field. Okay, so this is the basic requirement. You need to keep the ferromagnetic sample in an external magnetic field. Okay, now if you take some 500 years back, current, okay, moving charges gives rise to magnetism. So this was first observed by Ørsted himself, right? So before Ørsted, we did not know this, correct? So therefore they used Earth's magnetic field to magnetize the materials, right? Now later when we got to know about this, now stronger is the magnetic field, you have better alignment of the dipoles, correct? So therefore what we'll do these days is that we'll take a solenoid. Okay, we'll pass a strong current through the battery. So if current is strong, B is equal to mu naught Ni, right? So the magnetic field, right? So the magnetic field inside this solenoid, it will also be strong, right? So you can write like this. So this is B external, all right? Fine. So here we will keep the ferromagnetic sample. Now all of you know the story, right? So the samples, the magnetic dipoles, they will arrange in the direction of the external magnetic field. Okay, so this is the modern manufacturing process. All right, fine. Now what must be the nature of that material? Okay, which material will you select? There are so many ferromagnetic materials. Okay, now which material will you select means, so for making permanent magnets, you have to select a material having high retentivity. Okay, you have studied about retentivity, which is also called as remanence, all right? And second one, it must have high coercivity also. Okay, now what is the reason? You may guess the answer. It's not that difficult. Now what do you mean by retentivity? If you can remember this graph, so we got it something like this, correct? So this is the hysteresis graph, right? So this point B, we'll call it as the retentivity, right? Now what it means is, so this actually I wrote it wrong. Just a rough sketch. It has to be like this, right? So yeah, this, what it means is, even though you have reduced, so this is H and this is B, okay? Even though H is 0, you are seeing some magnetization, okay? That means when you take that sample out of the solenoid, you expect it to work like a magnet, right? So it must be having high retentivity, and also it must have high coercivity. So retentivity is this point B, and coercivity is this, coercivity is this point C. Okay, now why it needs to have high coercivity means, it's really simple. So when you keep this magnet, say this is the north and south pole of the magnet. Magnet is the same sample, okay, the same sample. Now it is behaving like a magnet. All right, now its magnetic field will be this way, correct? And if you can notice the arrangement of dipoles, naturally it will be this way. Okay, so notice the direction of the magnetic field, then you can notice the direction of the individual magnetic moments. Fine. Now say you are keeping it in the Earth's magnetic field. Say Earth's magnetic field is this way, right? Now due to this Earth's magnetic field, very few of these dipoles, they may actually try to align in the direction of the Earth's magnetic field, because the torque acting on the dipole, it will always try to bring that dipole in the stable equilibrium. Okay, so when the dipole is this way, okay, when the dipole is in the direction of the external magnetic field, we'll say it is in stable equilibrium. Is it not fine? Now, very few of them may arrange, but the remaining, okay, they have to point in the, they will point in the opposite direction, right? So what is coercivity? As I told you, it is the amount of, or you can say, you know, B in this case, at least for a solenoid, we'll write B is proportional to H, correct? So B is equal to mu naught Ni. So the same thing if you remember here. Ni itself, we wrote it as H. B is equal to mu naught H, right? Now this H, right? This H which is in the opposite direction, so that is what it means, right? H which is in the opposite direction, it has to be sufficiently strong to again disturb the dipoles completely so that the magnetization will become zero. Okay, so we need high coercivity. That means when this magnet is kept in an external, or you can say stray magnetic fields, unwanted magnetic fields. Okay, so it must not disturb the arrangement of the dipoles. Okay, it must not disturb the arrangement of the dipoles. So in this case, in this example, whatever I have drawn here, the Earth's magnetic field, usually it will not disturb the alignment of the dipoles. Even if it disturbs, it is very, very less. Okay, so therefore, if you buy a bar magnet or something, okay, now try to make out the north-south direction. So try to keep the that is the bar magnet, so that the net magnetic moment, you can find out the net magnetic moment it will be towards the north pole, right? It will be towards the north pole, fine. So that net magnetic moment and the Earth's magnetic field are in the opposite directions, let us say. You will not see any changes in the magnetism, okay? You will not see suddenly the magnet will actually reduce its attraction, okay? You can say the magnet, what can you say? The magnetic effect, right? So the magnetic strength, you can say, right? So the strength of the magnet, to put it in a simple words, you can say the strength of the magnet will not be affected. Okay, so that is why we choose high coercivity. Okay, so for example, if you look at this graph, okay, so if you keep this magnet in the Earth's magnetic field, you may be you'll be reaching almost this point. See, when you reach that point, you will see that you are having still some magnetic field, correct? So this point you can actually tell you that it is representing the magnetic intensity due to Earth's magnetic field. Okay, so just for an example I told, all right, fine. So that is why we will choose material having high retentivity. Okay, that means even after the current in the solenoid is made zero, otherwise as soon as you take once you take it out of the solenoid, it must behave like a magnet. Okay, so that is the main purpose of calling it as a permanent magnet, right? And the next thing is, even when you keep it in some space where you have some random magnetic fields, now those magnetic fields must not disturb the or you can say the magnetic strength of this permanent magnet. So therefore we choose the material, okay, the material for manufacturing permanent magnets to have, they must be having high retentivity and high coercivity. Okay, so that is one thing. Fine. Now for example, you can say steel, right? If you compare steel and iron, right? So you can say steel and iron are a good example for ferromagnetic materials. Fine. Now here the retentivity, okay, the retentivity of steel, fine, the retentivity of steel is less than the retentivity of iron. Okay, the retentivity of steel is less than the retentivity of iron. And also if you compare the coercivity, okay, if you compare the coercivity, so coercivity of steel, okay, coercivity of steel will be greater than coercivity, right? Coercivity of iron. Okay, so what is your best choice? See, retentivity, it doesn't matter. If there is some finite value for retentivity, obviously you can use it as a permanent magnet for some small applications where you need less magnetic field strength. Okay, so retentivity of steel is less than retentivity of iron, so that is not a problem. But what we need to make sure is that even though I'm telling you what is the best choice among steel and iron for manufacturing permanent magnets means we'll always go for steel. The reason is retentivity of steel may be less than retentivity of iron. That means some magnetization is present in steel even after you remove it from the solenoid. So that is a known fact because of the arrangement of dipoles, right? So hard ferromagnets we used to say, right? Fine. But the coercivity, if you observe, coercivity of steel will be greater than the coercivity of iron. So what it means is when you keep iron and steel, okay, say you are taking steel and iron, okay, parallelly, and you are magnetizing both of them, okay, and you will leave the steel and iron in some stray magnetic field, okay, some other magnetic field, right? Now you will see that some other magnetic field, stray magnetic field, it has a good chance of disturbing, or you can say this iron, okay, this iron has a high probability of losing its magnetism compared to steel, because steel has high coercivity. It needs the strength of the disturbing magnetic field, otherwise the stray magnetic field more, okay. So the strength of the stray magnetic field required, it is actually more, okay, for you can say for demagnetizing the steel compared to demagnetizing iron, okay. So therefore steel is a better choice compared to iron for manufacturing permanent magnets, okay. Now you need to remember this point, right? Now the other materials what we use for making permanent magnets is that, as you know, we have given an example already. So there is a alloy called as alnico, okay, aluminum, nickel, cobalt and iron also we'll use, right? And there is something called as cobalt steel, okay, cobalt steel we'll use. And third one, we have something called as ticonal, okay, so TICONAL, okay. So they say this ticonal, it has all the contents present in the alnico, all right, aluminum, nickel, cobalt, iron, and apart from that it has little bit of titanium, okay, it has little bit of titanium. And yeah, let me show you. So yeah, ticonal alloy, yeah, nickel, cobalt, aluminum, copper and titanium, okay, they'll use apart from this nickel, cobalt, aluminum, copper and titanium, all right. So just know this, fine, all right, okay. Now that is what this is one more example for you. These are the three examples for hard ferromagnets, okay, hard ferromagnets, or the materials what you can use for manufacturing permanent magnets, okay. Now next let us go for electromagnets, all right. Now I think you know about this electromagnets, it's really easy. So electromagnets, as the name itself says, we do not want them to behave like permanent magnets, okay. So electromagnets, what it basically it means is, as long as you have a flow of current, okay, as long as current is present, so you must be, that electromagnet must behave like a magnet. When current is zero, so the magnetic field must also become, it should become zero. So this is the main purpose of electromagnets what we use, right? Fine. Now the characteristics or the properties, you can say the properties of the materials which can be used for manufacture, or you can say which can be used as electromagnets, is that they must have high permeability, okay, they must have high permeability, and they must have low retentivity, because as soon as current becomes zero, I need B to become zero, right? So they must have low retentivity, correct? I think all of you have seen electromagnets, right? So they will use it especially in the recycling plants, correct? So say you have, I think all of you would have seen that there will be an old car, they'll try to lift the old car and some metal scraps, right? Now if you use permanent magnets there, what is the use? So that scrap will always be sticking to that permanent magnet. So they will be using electromagnets. So there will be a crane. To that crane you will attach this electromagnet, all right? So this will be the electromagnet. So say that there will be wires, of course, through this, right? Now once I is not zero, so you will see some magnetic field here which is not zero, so therefore it will attract all the metal scraps and everything. Now that person, he'll take that electromagnet to, he'll move the crane and he will reduce the current, he'll switch off the current. Once current is gone, Once current is 0, so obviously magnetic field will become 0 and all that metal scrap will fall down. Okay, all of you have seen this, right? So this is the main purpose of electromagnets, right? Yeah. Now other, you can where else we'll use this electromagnets is that you can look at the applications. So we'll use it in electric bell. We have it in our school bell, right? So electric bell. So it is basically used as a switch. All right. So what is that mechanism? You can think. Then loudspeakers. Okay, loudspeakers. Fine. So obviously you'll be, what do you connect to your loudspeaker? You will connect two wires, right? What are we using those wires for? For current, right? So when current flows through them, right? So it will be having varying signals. Okay, it will be having varying, it will vary, right? It is not a constant current. So since it varies, so you'll be having a small electromagnet which will be in the loudspeaker, right? So these loudspeakers, they will do in and out motion. So that is how you can hear voice. You can hear my voice right now. All right. So that is, we'll use it in loudspeakers, and we'll also use it in telephone diaphragms. Okay, diaphragms.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is and how they work, then this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use. The paper electromagnet in this video was just for a demonstration, but you should not try this at home because the paper could actually catch on fire. To see a variety of science projects that use electromagnets, as well as instructions for thousands of other science and engineering projects, visit us online at www.sciencebuddies.org.
A relay is an electrical switch. So again, it's a switch, but this is not automatic switch. So it's a switch that open and close under the controls of another electrical circuit. So we use the circuits to open and close a switch. And the switch is operated by electromagnet to open or close one or many sets of contacts. So this is an electromagnetic relay. And from here you can see that the length is about 3 cm, 2.5 to 3 cm. Okay, and then you can see that there's an electromagnet here. There is a input output here. Okay, The switch is here. Okay, I'm going to explain to you how it works. Okay, so this is the illustrations of an electromagnet relay. Electromagnet relay. Usually, inside an electromagnet, there is at least two circuits. At least two circuits. It can be more than two circuits, but at least it must have two circuits. First, you see, there's a circuit here. This is a circuit that controls the electromagnet. And then we have the second circuit. Okay, the second circuit. So usually this one is connected to the electrical appliances. Now usually this one is connected to a very high voltage current. Very high voltage currents. So if this is connected to a very high voltage currents, a few thousand volt, so it's very dangerous for us to switch it on and off directly. Okay, it may cause this electric shock if you try to switch it on or off directly. Okay, let's say the switch here. So if you try to switch it on and use your hand to switch it on or off here, it's very dangerous. So therefore, we use another circuit to switch it on and off. Okay, we use another circuit to switch it on and off. Okay, so what we do is we use this one. This is called the first switch. This is called the second switch. So let's see. We switch this on. We switch this on. Now after we switch this on, there's current flow. Yeah, current will flow in this wire here. Inside this wire, there's current flow. And when the current flow, then this thing, it will become a magnet. Okay, it will become a magnet. And if it become a magnet, it will pull this iron armature. It will pull the iron armature. You pull this iron armature. Now let's see what will happen if this iron armature is pulled by the magnet. Pulled by the magnet. Okay, so if it's pulled by the magnet, it will push this switch. Okay, so try to see. Initially, it's disconnected. It's not connect. It's not connect. But if we switch this on, this become a magnet. It pull the soft iron armature. It will push this end up and connect the second switch. Okay, and when it connect the second switch, okay, then the current flow in the second switch. Okay, then it will make the machine operate. Okay, the machine operate. And of course, if you switch it off, okay, if you switch it off, there's no current flow. Okay, then it will go back to the initial positions. Okay, it will go back to its initial positions. Okay, that's how it works. You switch on the current flow, you pull the iron armatures, and then the second switch is on. Okay, telephone earpiece. Telephone earpiece, how it works. An electromagnet is used in earpiece of a telephone. So this shows illustrations of the telephone earpiece. Let's say your friend give you the call, a phone call. Okay, not handphone. Okay, the house phone. Your friend give you the call. So when your friend give you the call, so when he talk, okay, he talk through the phone. The phone has an earpiece and a speaker. The phone has earpiece and speakers. So when he speak, the speaker will convert the sound energy to electric current. So when your friend speak, so the speakers will convert the sound into electric current. Okay, and that's called the mouthpiece of the telephones. So these currents produced will change, increase or decrease according to the frequency. According to the frequency. So these currents will increase, decrease. Okay. Then this currents will flow to your house. So of course the telecom will do his work. Okay, to send this electric currents from your friend's house to your house. So when these electric currents move from your friend's house to go to your house, and remember the currents will increase, decrease. Okay. The current will flow into this magnet here, and when the currents increase, decrease, there's a soft iron core here. So when the current increase, this will become a strong magnet. When the current decrease, it will become a weak magnet. So the magnetic field here will also increase, decrease. So when the magnetic field here increase, decrease, it will pull this diaphragm. This diaphragm is a ferromagnetic materials. Usually it's an iron also. Irons. It's very thin. It's very thin, but it can pull by the magnet. So when the currents increase, decrease, it will cause the magnetic field here also increase, decrease. So when the magnetic field here increase, decrease, it will pull. When it increase, it will pull the diaphragm. Okay. When it decrease, it will let go the diaphragm. So this diaphragm, it will vibrate. Okay. It will vibrate when the current increase, decrease. Okay. And remember, the current here, the frequency of the current is the same as the frequency of the sound of your friend. Therefore, the diaphragm here will also vibrate as the same frequency of the voice or the sounds produced by your friend. So when you, of course, this is not very loud, so therefore you must put your ear very close to this earpiece. Then you can hear the voice of your friend. Okay, the voice of your friends. So that is how it works. That's how it works. Your friend talk to the mouthpiece. So the mouthpiece change the sound to electric currents, and the electric current is sent to your house, and then the electric currents produce this magnetic effects on this electromagnet. Okay, these electromagnets will cause the diaphragm to vibrate, and when it vibrates, then it will change. It will produce a sound again. So that is how it works.